We considered M in B of H a von Neumann algebra with a vector psi 0 in H, bicyclic. And for a psi in H, we defined when it is preclosed an operator L psi, which is L psi restricted to M prime psi 0 closure, and L psi of x prime psi 0 is equal x prime psi. And this operator L psi is obviously affiliated to M. It commutes with all the operators in M prime. Then we defined a cone PS, which are the Xi in H, such that L Xi is positive, which is the same thing as those Xi in H, so that the vector form on the commutant Xi naught, it's positive. And finally, this is equal to A psi 0, where A is affiliated to M, is positive self-adjoint, and psi naught belongs to the domain of A. Okay. Similarly, were defined the operators Rn and the cone PS star. Okay, and then what we proved? We proved the following thing, that I didn't prove, but I stated this, and it is a simple proof. R equivalent the following statements: a vector psi belongs to PS, or psi is in the domain of S of psi is equal to psi, and L psi is positive. 3 is the fact that psi belongs to M plus psi 0 closure. And the fourth condition was that psi scalar product with eta is positive for every eta in PS star, the other one. Of course, the same thing will be here. R equivalent J, eta belongs to PS star. Similar assertion with S star in here, and this is eta belongs to M prime plus psi naught closure. From this, it follows that this and this, it follows that J PS is PS star, because psi 0 is left invariant by J, and J is M prime. So that I have this thing from which we obtained that delta 1/2 PS is PS star, and finally that delta 1/4 PS it's equal delta minus 1/4 PS star. So that in particular the closures of this are equal, and this is denoted by P. It is in the middle, say. Now, what are the goals? If you have a psi in P, then you have J psi is equal to psi. Okay. Now the goals are the following. The fact that if you start from P with a vector psi and you go to the vector form omega psi in M star plus, this is a homeomorphism. With respect to the norm topologies. So that if you have a form phi in M plus substar, then there is a unique element in P, I call it phi 1/2, such that in P, such that phi is omega phi 1/2. Consequence of this is the following. If you have phi and psi in M star plus, and you have that phi is less than psi, this means that omega phi 1/2 is less than omega psi 1/2. They are the vector states on M. But because of the fact that J of psi is equal to psi for psi in P, this is the same thing as saying that omega prime phi 1/2 is less than omega psi prime 1/2 on M prime, right?
What is phi to the 1/2?
Is the unique vector here, which makes for every phi positive normal, there is a unique vector phi 1/2 in P such that phi is equal omega phi 1/2. Okay. It was a notation, but that, because phi 1/2 is in P and G psi is equal to psi, and on the other hand, GMG is equal to M prime, it follows from this thing, it follows that also these vector states regarded on M prime are in the same relation. And then what follows? It follows that there exists a unique element X in M such that the vector phi 1/2 is equal to the operator X applied to the vector psi 1/2. And namely, this operator X is defined as usually X on every X prime psi 1/2, it's equal to X prime phi 1/2. And also X prime is equal to 0 on M prime psi 1/2, M prime psi 1/2 orthogonal. This is the operator X, which makes this relation. This operator X is denoted by d phi over d psi and is called the spatial derivative. This spatial derivative obeys the chain rule. That means d theta over d psi is equal d theta over d phi times d phi over d psi. That's obvious because of this relation here. Now,
This is when all of them are faithful.
no, are phi and psi. Yes, if you like. But it's enough to put psi fightful, and then the support of theta is less than the support of phi. And then this still holds. Okay, Professor Takesaki said that he will use the spatial derivative. For that reason, I said this. This is the first goal, and a second goal is the following thing. If you have, say, sigma, an automorphism of M, this you have a unique U sigma and unitary in the space H, such that sigma is add of U sigma. U sigma J is equal J U sigma, and U sigma P is equal to P. So there is a unique unitaries with these properties. That's the canonical implementation of automorphism. Now, here you have the VO or SO topology. The two topologies coincide on the group of unitary elements. And on the other hand, here, on the automorphism of M, you have uniform convergence on the predual. That means U sigma I, phi composition with sigma I minus phi composition with sigma in norm converges to 0. And that's for every psi, or every phi. So this is the canonical implementation, and it's an important fact that the topology of uniform convergence on the predual in automorphisms of M is the same as the strong operator or heroic operator topology on the unitary group of H. For that reason, this topology is called the natural topology on the automorphisms. So the natural topology of the automorphisms that has been used by Professor Takesaki was the uniform convergence on the predual. And that's all for what we will have to do. But the way to arrive at this result is rather intricate. And so I will begin today the proof of them, and I will finish in the last day on Friday. Okay. Now, I will introduce a notation which is very convenient. Namely, let's put xi is equal x psi 0, and eta it's y psi 0, and they belong to M psi 0, which corresponds to the left Hilbert algebra A or A second in the case of the bicyclic vector. And then for this, I will denote this. Xi times eta is L xi of eta. That means multiplication by xi applies to eta. And this means nothing else than x, y, psi 0. And again, for psi is equal x prime, x prime psi 0, and eta y prime, y prime psi 0 in M prime psi 0, which is A prime. We will denote again psi eta is equal to R eta psi. That means exactly the same thing is equal to x prime, y prime, psi 0. The notation is very convenient, and of course, if you have psi and eta in the Tomita algebra, for instance, then the two definitions coincide. Okay. Now, what we have seen in here was that PS it's equal to m plus psi 0, and that means this is psi times s psi when psi is in a second. Well, this is x star x, right? Is x star x, so a positive element from m plus m psi 0. And on the other hand, the other cone PS star is equal to.
You make a closure on the.
Yeah, thank you. And the other thing is eta S star of eta when eta belongs to A prime. Now, by the usual approximations we used for the Tomita algebra, we can see that this is also equal with the same thing, but this in the Tomita algebra. And also here, the same thing, but in the Tomita algebra. Yeah, thanks. And in the Tomita algebra. Okay. Let me recall also some easy things, namely for psi eta in the Tomita algebra, we have delta alpha psi eta is equal delta alpha psi delta alpha eta. And j of psi eta it's equal to j eta times j psi. Okay, so that if I have a psi in the Tomita algebra, I will have delta 1 over 4 of psi times s psi. It's equal to delta 1 over 4 psi times delta 1 over 4 of s psi. But this means nothing else than delta 1 over 4 psi times j of s of delta 1 over 4 psi. Let me show why is this. What you have here. You have delta 1 over 4 times s. S is delta minus 1 over 4 j. And then, if you apply this to delta 1 over 4.
Second term is delta or minus half.
Sorry?
Second term is delta or minus half.
Yeah, delta minus 1/2 j. This is delta minus 1 over 4 j, which is j delta 1 over 4. And that's the reason for that. Okay. We have that delta 1 over 4 of the Tomita algebra is the Tomita algebra. So if we denote by P0 the set of all psi times j psi for psi in the Tomita algebra, we will get that delta 1 over 4 of P0s it's equal to P0. Okay, and then similarly delta minus 1 over 4 P0s star it's equal to P0. I'm sorry, put 0 here. Okay, now it follows that this is not completely trivial. It follows that P, which is the closure of P, is, well, 0, I put here, of P is 0, namely it is zeta times j of zeta when zeta belongs to the Tomita algebra and closure. Well, let me give the proof of this, because delta 1 over 4 is not a bounded operator, so that I have to do some more precise things. Indeed, if I take a xi in PS, then I get a sequence Cn in PS0. Do I have still this notation? Xn converges to Xi. Well, it is before the closure in here. P0 is before the closure in this thing.
Excuse me, do you mean that this set, the polar,
It's not a polar, no, it's a notation.
This P is equal to something like x, j, y0.
Yes, for instance, yes, indeed. Yeah, it's x, if you take zeta is an A0, this is A times J, AJ, say 0, which is, right? Is what you asked. Okay, so I take a sequence Xi n in here so that they converge to Xi. And what I have that S of Xi sub n is equal Xi sub n, because it is in m plus Xi 0 in there. Okay, then I have also S Xi is equal to Xi. And because delta 1/2 is equal to Js, I get that delta 1/2 Xi n converges to delta 1/2 Xi. Okay, because delta 1/2 is on these elements is just J, because S of them is the same thing as them, and J is a bounded operator. Therefore, what we get that delta power 1 over 4 Xi minus delta power 1 over 4 Xi n. This is equal to delta 1/2 Xi minus Xi n times Xi minus Xi n, and this converges to 0, because this converges to 0, as we've seen. Okay, so that it follows that delta power 1 over 4 of Xi belongs to the closure of delta 1 over 4 PS0 closure, which is P0, this one here, closure. Consequently, it follows that P is included in P0 closure by the definition of P. And then the converse is obvious. Converse P0 is equal to delta 1 over 4 of P0s, and this is included in delta 1 over 4 of Ps, which is included in P. And so that you have the equality, so that indeed I have this equality I wrote here. I wrote here P is the closure of psi j psi with psi in the Tomita algebra closure. Okay. And again, with approximation from the Tomita algebra, we get that P is equal to psi times j psi for psi in a second. That means in m psi 0 closure, and is the same thing as being j of eta eta for eta belonging to a prime, which is m prime psi 0 in our case. And you have the closure. Okay. Now, it's clear that if you have zeta in P, you have that j zeta zeta is equal to zeta. Okay, and now what we have the following thing, that delta power it of j of zeta j of zeta, again for zeta in the Tomita algebra, in this is equal to delta power it zeta times delta it j, but this means delta power it j, that means j of delta power it of zeta. Okay. You have this thing. That means that delta power it of P0 that was there up, it's included in P0. And because this is a bounded operator, it follows that delta power it P, the closure of this, it's included, and hence it's equal to P, because you can use also delta power minus it. So that this is another conclusion. And now, let me put it somewhere here in order to. I will have that if zeta is in P, and if f, if an integrable function on R, which is positive, then also you will have integral from minus infinity to infinity of f of t delta to power it of zeta dt also belongs to P, because P is closed and is a convex set which is closed. It's a closed convex cone. Okay, now what we show now is the following thing, that if x is in M, then I have x times j x j belongs of P is included to P. It's the cone. Namely, take an xi in a second. It's equal to m xi 0. Well, you may wonder why I insist to put a prime a second. Because the proof is the same in the general case. Here, a second is just m xi 0. But I write it so in order to show that the general proof works in this manner. In the case of a weight, not a... Okay, and take a zeta in the Tomita algebra. Then we have the following thing. We have L xi times j L xi j applied to zeta j of zeta is equal to L xi j L xi. And this, what I put here, is equal to j L xi j L zeta, I'm sorry, j times zeta. Okay, now this is because of the commutation. What is the commutation? The commutation will be, well, I write what it is. It's L psi j. And now you have these two things, this one and this one. This is in the algebra M, this is in the commutant. So they commute. So this is L xi j times j L zeta j, which then is L xi applied to zeta. Okay, they commuted there. And this is here, you cancel this. So what you have it's equal to L xi, then is L zeta, and then is j L xi of zeta, which means this is exactly xi zeta, that means xi zeta times j of xi zeta. And it follows that we have L xi j L xi p of p. It's included in P, and therefore also with closure, because these are bounded operators. Now, second, so this is an important thing. Now, what I will show that the P is a self-polar cone. That means that if you have xi such that xi eta is bigger than 0 for every eta in P, then necessarily xi is in P. Okay. Indeed, take a xi in P sub S and an eta in P sub S star. And then we have delta 1 over 4 xi, delta minus 1 over 4 eta is equal to xi eta. Of course, this goes by adjunction. And this is bigger than 0 because these two cones were polar to each other. So this means, by the definition of P, it means that this implies that if you have psi in P and eta in P, this implies psi eta is bigger than 0. Because this one is in P and this one is also in P. If Xi is in PS, this is in P. If eta is in PS star, this is in P. And they are a generic set. That means you obtain the whole P by closing delta 1/4 of PS. Okay. So that indeed we have this thing, and now we have to show that conversely, if such a thing happens for every eta, then Xi belongs to P. Okay. So let zeta in H be such that you have zeta tensor product with eta, scalar product with eta is bigger than 0 for every theta in P. Okay. And denote by zeta n, it's equal to root of n over pi, integral from minus infinity to infinity, e to power minus n t square, delta power it, zeta dt. And also theta n, the same thing with theta. That means it's root of n over pi, the integral from minus infinity to plus infinity, e to power minus n t square, delta power it of theta, dt. Okay. Now, if theta belongs to P, then also theta n belongs to P. I think it was there, this thing. And consequently, what we have that zeta n scalar product with theta, that's obvious, this equality, namely this is theta n. And this is bigger than 0. In particular, what we get that if Xi is in P sub S, then delta power 1/4 Xi is in P, and then we have delta 1/4 zeta n times Xi, it's equal zeta n times delta 1/4 Xi, which is bigger than 0 for every n belonging to n. That means the following thing. It means that delta power, we see, this one times with every element Xi in P, S, was positive. That means that delta 1/4 zeta n belongs to PS star, because the cones PS and PS star were dual to each other. Then it follows that zeta n belongs to delta 1 minus 1/4 of PS star, which is in P. And now zeta n converges to zeta. So zeta belongs to P because P is closed and is a convex cone and everything you have. So that indeed the P is a self-polar cone, convex cone. P, self-polar, closed, convex cone. Here. Now, if you have theta is in P intersection with minus P, then you have theta times minus theta. Both of them are in P, so that this is bigger than 0, so that theta is equal to 0. Okay, being equal to 0, it means that this P intersection minus P, it's reduced to 0. The second thing in here. Now annotation. If you have theta, it's equal j theta, and if you have theta is equal j theta, then you will write theta is less than theta, that if and only if theta minus theta belongs to P. So that this is an order relation of J invariant elements, which is defined by this cone. Good. We will prove now that this cone generates by linear combinations the whole H. And namely, what we show that if you have a theta in H such that J theta is equal to theta, then there exist unique elements theta plus and theta minus in P, such that theta is equal theta plus minus theta minus, and theta plus is perpendicular on theta minus. Okay. How to do this thing? Just take such a theta, and then because P is a closed convex set, it means there is an element of minimal approximation, of minimal distance. That means I will take theta plus in P such that theta plus minus theta in norm is the infimum of norm of theta minus theta for theta belonging to P. And then we denote theta minus is equal theta minus theta plus. So that this thing, theta minus, what I put here, theta minus theta plus. And then I should have this equality. Where is the negative sign? No, sorry. Y plus, theta plus, minus theta. That's okay. And so this thing is clear. Theta plus is in P. What we still have to show is that this belongs to P, and that theta plus, theta minus are orthogonal. Okay. Now, take any theta in P and any t positive. Then, because of this minimal choice, I have the following thing, that this is bigger than 0. That means is theta plus plus t theta, the argument is rather classical. Minus theta. This thing is bigger than theta plus minus theta, because this is the infimum. Okay, and if you make here the computation, you get here is t square norm of theta square minus plus 2t real part of theta minus theta. And because t bigger than 0 was arbitrary, it follows that by cancelling with one t here, so that you will have that this is bigger than 0 if you cancel a t. Okay, and this means that real part of theta minus times theta, it's bigger than 0. Now, what I have j of theta minus, it's equal theta minus. And on the other hand, j theta, it's equal to theta. So that what we have that theta minus times theta, it's equal to, it's a real number, and namely a positive number, theta minus theta, which is bigger than 0. Okay. And hence, this follows from this, and the fact that theta was arbitrary, it follows that theta minus belongs to P. On the other hand, we have the following thing for any t in 0, 1. We have that norm of 1 minus t theta plus minus theta square minus theta plus minus theta. This is again bigger than this, so this is bigger than 0. And this is equal to t square theta plus square minus 2t real part of theta plus theta minus. So this is again bigger than 0 for any t, and that means that real part of theta plus theta minus, real part of theta plus theta minus from here, it's less than or equal to 0. But this one is positive. So that indeed theta plus theta minus is equal to 0. That means this thing. So that we have that H is the linear hull of P. Every element in H is of the form theta 1 minus theta 2 plus I theta 3 minus theta 4 with theta k in P. Okay. Good. Now, a definition. We say that the von Neumann algebra M in B of H is hyperstandard if there exists J, a conjugation on H, and P in H, a self-polar cone such that we have the following things. The map from M, X, going to J, X star J in M prime is a star anti-automorphism. This is the first condition. The second condition is that if psi is in P, then G psi is equal to psi. And third condition is that if X is in M, then X times J X J of P is included in P. That for every X in M. So that standard meant just this thing, but I forgot to add also here one thing, acting identically on the center of M. So the fact that M is standard means just the existence of the conjugation such that this holds. Hyperstandard means to have also a self-polar cone included in the set of fixed points for G, for J, and moreover this thing, this condition. Well, what we've seen that if we have a psi 0 bicyclic vector for M, then we get in a natural manner J and also the P we introduce it so that every von Neumann algebra is isomorphic with a hyperstandard von Neumann algebra. But on the other hand, when you say that M is hyperstandard, you don't mean anything bicyclic vector or left Hilbert algebra or so, you just mean this thing, so that J and P are connected to M by definition, to the hyperstandard thing by definition. So that it will be natural. Let me see if this is the thing well, I would like to go directly here. If I get stuck, I will come back in this. We have this hyperstandard von Neumann algebra. And moreover, you assume that there is a bicyclic vector in H, right?
Can you multiply two elements in P?
Sorry?
Can you multiply two elements of P?
I mean, is there a way to multiply two elements in P? You have written X, J, X, J, P is inside P.
But it's not, these are elements in M, these are operators. These are operators applied to vectors. So this is an operator in M. And then you multiply the operator X with the operator JXJ, you get here an operator, and you apply this operator to vectors. So you get vectors. Is that okay?
Suppose we are representing the von Neumann algebra with respect to a faithful normal state.
Yeah.
So then your cone will look like a x, j, x, j times the cyclic vector closure, right?
Yeah.
Right. So can you not multiply? Then I can kind of
If you want, well, I think that this thing here is settled. So you apply operators to vectors. On the other hand, you ask me what means if you have psi and eta in P, what means psi eta? Psi eta means what I said at the beginning. It depends. At the very beginning, I said it is a notation. If you have psi and eta in A, that means in M psi 0, then psi eta is the left translation operator applied to eta. That means if you take this is x psi 0 and this is y psi 0, then psi eta means x, y, psi 0. So that this is not, here is not such a problem. Here is just the fact that x, j to be what we have seen already. Okay. So that, let's assume we have a hyperstandard von Neumann algebra, and we have also a bicyclic vector, right? This bicyclic vector associates to M a conjugation, I will call it J0, and a self-polar cone, I call it P0. What I have to show now, I want to show now, is that J0 is equal to J, and P0 is equal to P. That means if you have a bicyclic vector, then the only possibility for the algebra to be in hyperstandard form on that Hilbert space is just with these things associated to the bicyclic vector, right? Okay. Good. The self-polar cone P0 is x J0 x J0 times psi 0 when x is in M, and I take here the closure.
Sorry. Suppose you have a second bicyclic vector, C and C1 and C2.
Yeah.
Each of them would give you a hyperstandard.
Yeah. So that.
Are you saying that?
Yes, I am saying that you will have the same J0 and the same P0, right? Okay. So that's in particular, of course. But here, P and J are just abstract, right? These ones are concrete things. So that what I want to show is this thing here. And then I will take an x in M. Then J, x, J is in M prime. Consequently, I have the following thing, that J, S0 star J, notice J is the abstract J, S0 is the concrete S associated to psi 0. What?
In the second bicyclic vector in the cone?
No. This is an abstract definition. You have a J and a P given by this definition. On the other hand, suppose you have a bicyclic vector in H, bicyclic for M. Then, this bicyclic vector gives rise to a conjugation J sub 0 and a self-polar cone P0 as we have seen up to now. The assertion is that the abstract J here is just exactly this J0, and the abstract P cone, self-polar cone, is exactly this cone we associated to the...
For any bicyclic vector.
I take a bicyclic vector. If you take another bicyclic vector, you will get other J0 and P0, and they will coincide. also there. Is that okay? No?
Yeah. No, but you might get the J's are different.
So I might get what?
J, modular conjugation operator.
He is saying you won't.
He's saying it is unique. It's the same J, same P.
In particular, if you have two bicyclic vectors, you will get the same J and the same self-polar cone. Right? Is okay now? Fine. Okay, so that I take an x in M, then this is in M prime. And what I have J S0 star J applied to x psi 0 is equal J S0 star J x J psi 0. Okay. Now, this means, because this is the original thing, this is equal to J x J star psi 0. And this means is equal to J times J x star J say 0, and this is equal to x star J say 0. And this disappears because you assume that J acts on J on psi 0, so I have to assume J psi 0 is equal to psi 0. So that I got this thing, and that means that the operator S0, which associates to x psi 0, x star psi 0, is included in this operator, which means J S0 star J. Similarly, you obtain that S0 star is included in J S0 J. And then you have equalities, and this means that J S0 is equal to S0 star J. And this means the following thing, that J S0 star it's equal to S0 star J, it's equal J S0. So this is self-adjoint. Okay, and now for x in M, we will have the following. For x in M, we will have the following equalities. J S0 applied to x psi 0.
Sorry, Serban.
Yeah.
Sorry to keep butting in. The J, why is J psi 0 equal to psi 0?
I have to put it in as an assumption.
So psi is a bicyclic vector?
Yes, I have to assume that J psi 0 is equal to psi 0.
When you take this,
When I take, when you take the, so I take a psi 0, bicyclic, but in P, 0. Okay. So that from the beginning I take it from, and then I have J psi 0, it's equal to.
this is what he was asking. This is what he was asking earlier.
Yeah.
Is psi 0 in the core?
Yeah. So that what I obtain is JS0 x psi 0 times x psi 0. This is equal to J S0 x psi 0 is x star x psi 0 times x psi 0, which is further equal to x j x psi 0 psi 0. and which is further equal to x j x j x. I put j xi 0 in here. I put xi 0. So I put a j here. J of xi 0 is equal to xi 0 times xi 0. And this thing is bigger than 0 since both sides are in P. So let me make clear here. What I assume that I have a xi 0 in P, the abstract P. And then I have j xi 0 is equal to xi 0. Both sides are in P, so this is bigger than 0. And now, if you have, you see that this is bigger than 0. Now, JS0, JS0, it's equal JS0 restricted to M psi 0 closure, right? So it follows that this operator is positive, right? J psi 0, X psi 0, X psi 0, X psi 0 is bigger than 0. Okay, now what I write the following thing. S0 is equal to JS0. That's a triviality on one hand, but on the other hand, this is a polar decomposition because this is indeed a conjugation, and this one is a positive operator, so that by the uniqueness of the polar decomposition, I get that J here it's equal to J0, which is the the unitary operator appearing in this thing, J0 delta 0 power 1/2. This was the polar decomposition at the beginning. This is another polar decomposition, so that J is equal to J0. Okay. And then we finish quickly. Then P0, it's equal to X J0 X J0 Xi 0 when X is in M. It's equal with the same thing, X J X J Xi 0 for X in M. You take the closure. This was the closure. You have the closure in here, and this is included in P, the abstract cone. But because P0 and P, both of them are self-polar cones, then you have that indeed P0 is equal to P, and this ends the proof. So let me answer again some questions were put here. You have to assume not only that psi 0 in H is bicyclic, but psi 0 is in this abstract P, right? So that if you have another bicyclic vector in this abstract P, you get the same thing. But thank you, you made me to correct this thing. You have to assume that psi 0 is in P, and we use this very much in the form that J psi 0 is equal to psi 0. And that was the thing.
So there is no uniqueness in this hyperstandard form?
It's more than uniqueness, you will see. Namely, if you have two hyperstandard forms, there is a unique operator, unitary operator that implements the equivalence of them. So not only it's unique, because it's unique as a standard form, but is uniquely unique. That means there is a unique implementing of unitary operator, which exchanges everything in the definition. So, I have a quarter of an hour more, right? We will see what we...
What is an example there which is hyper standard but not standard?
Yeah, there are examples, and such an example was given by Hagerup. There are examples of standard von Neumann algebras which are not hyperstandard. And the example, I don't know it now, but I know that an example has been given by Hagerup. And by the way, I should mention that what I'm doing here follows the papers of Alain Cohn, Uffe Hagerup, and also Araki worked in this hyperstandard form. Actually, he introduced a family of cones, P lambda, but I will not have to do with that
What is the
thing.
notation hyper standard who introduced? I think this.
No,
Kakisakis.
no.
He called
This,
hyper standard as a standard.
the hyper standard denomination terminology was introduced by Hagerup. And I'm following here one of his articles. Okay. Now, a lemma. I have to show that the mapping phi, which takes an A to delta 1 over 4 A xi 0, is an order isomorphism between A in M self-adjoint and vectors xi in H, such that there is a lambda bigger than 0, so that you have minus lambda xi 0 less than xi less than lambda xi 0. So I have to show that this is an order isomorphism. Okay. Now, delta 1 over 4 is injective because delta is non-singular. Psi 0 in H is... No, for the moment I'm looking in this thing. M in B of H and psi 0 bicyclic. And the J and P are associated with this situation.
So when you say psi 0 less than or equal to some lambda psi 0, what does that mean?
What means the inequality here? No, the inequality is given by the cone. By the cone. So the inequality is there. Is by xi, j xi is equal xi, such that. Okay.
The cone of psi 0.
The cone of psi 0 gives an order. And then this is the order I put there. I didn't put here this thing because once you see the inequalities, all the fellows there should be invariant under xi, under j. Okay, delta 1 over 4 is injective. Xi 0 is separating. And then the map phi, this implies that the map phi is injective. If you get this is equal to 0, it means that A xi 0 is equal to 0, and because xi 0 is separating, it follows that A is equal to 0, and that's the whole thing. Okay, now take an A, self-adjoint in M, and we have A is bigger than 0 if and only if A xi 0 belongs to PS. By the description of PS we had at the beginning. And then, if you like a more detailed argument, PS is M plus xi 0, but is also A xi 0 with a self-adjoint operator positive having in the domain xi 0. Then A will coincide with A and hence will be positive. So this is and this is if and only if delta 1 over 4 A xi 0 belongs to P. Okay, by the definition of P as delta 1 over 4 of PS closure. Okay, that means that the map phi is injective and is an order isomorphism. This is positive and this is positive. So that is an order isomorphism. Now, take again a self-adjoint element in M, and then we have the following thing. 1 plus delta 1/2 of A xi 0, it's equal to A xi 0, that's the identity operator, A xi 0 plus, well, I will put first delta 1/2 of A xi 0, but A is self-adjoint, so it is S of A xi 0. And S is delta minus 1/2 J, among other things. So that here I have J, A xi 0, right? Correct. And from this thing, it follows that delta 1 over 4 of A xi 0 is equal to delta 1 over 4 plus delta minus 1 over 4 minus 1 of A xi 0 plus J A xi 0. Well, it's rather simple to see this thing, because this one here is equal to this one in here. And then you have to apply delta 1/2, that means, let me make some, delta 1 over 4, t to power 1 of 4, plus t to power 1 over 4 minus 1 over 4. This is to power minus 1. And you apply it to this thing, that means to 1 plus t to power 1/2. So what you get this is t to power 1 over 4. Take t a positive number. Then make this computation. And check that indeed is T over 4. This is enough as an argument by functional calculus that we have this equality in here. Okay. Now, this operator here is bounded, so that it follows the following thing, that if AI converges to A, this strong operator or weak operator doesn't matter because they are self-adjoint. And this happens if and only if phi of AI converges to phi of A. This happens in the Hilbert space and is weakly in the Hilbert space. Okay, I will say just this implication. It's important. Good. Now the set A in M such that 0 less than A less than 1, this set is V compact. Hence, phi of this set, this one is in H and is weakly compact. Now, take xi in H, jxi is equal xi, and 0 less than xi less than xi 0. I want to show the surjectivity. It's enough to show the surjectivity on this set in here. And then I have an element xi n, which is still bigger than 0. That means in P. It's equal to root of n over P, integral from minus infinity to infinity, e to power minus n t square, delta power I t, xi, dt. This is less than the same thing if I put here xi 0. Is less than the same thing with xi 0 in here, because xi is less than xi 0, so that xi 0 minus xi is in P, so that this thing applied to xi 0 minus pi is in P because P is closed and convex. Okay, and so this thing, okay, but if you put delta power it of xi 0, delta of power it of xi 0 is ever xi 0, and then you have to do just this integral, and you have the normalization here, which gives you that this whole thing is 1. So that what you get that this is less than xi 0. The xi ends in here are less than xi 0. Okay, good. Now, take an eta in the cone associated to S star. Then you have delta minus 1 over 4 of eta is in P. Hence, what you have delta minus 1 over 4 Cn times eta. It's equal to Cn times delta 1 over 4 of eta. I'm sorry, mine is self-adjoint. Minus 1 over 4 eta. And because this is in P and Cn are also in P, it follows that this is bigger than 0. This is positive. So that we see that this is positive for every eta in PS, and by the polarity between the cones PS and PS star, we have that delta minus 1 over 4 of psi n belongs to PS. Similarly, we get that psi naught minus delta power minus 1 over 4 of psi n. Also this one, which is equal to delta minus 1 over 4 of psi naught minus psi n, also this belongs to PS. This equality accounts for the fact that this belongs to PS in a similar manner as we did here. Okay, now, from this, it follows that the operators L0, say, of delta minus 1 over 4 of psi n, and it's positive, and the operator identity minus L0 delta 1 over 4 of psi n, which is L0 of this vector in here, which is psi 0, minus delta minus 1 over 4 of psi 0 of psi n. Also, this is positive. Okay. So I have that this. Notice that L0 means the operator of left translation before being closed. It has nothing to do with the formal notation with 0 in this. These are positive. And consequently, the operator AN, which is equal to L of delta minus 1 over 4 of psi n, this operator is bounded and is between 0 and 1. Now, Cn, it's equal to phi of An, and phi of f of An, which is psi n, this psi n converges to psi, because psi n was defined with that integral there. And now we know also that the set phi of A in M self-adjoint no, A in M 0 less than A less than 1, we know that this set is compact. So it's closed. So that psi belongs to this set. And that's the end of the proof. Namely, we showed that if I take an element like here, then psi, it is phi of something. That's enough to prove that the map phi is surjective on this set. And this is the end of the proof of the lemma, the end of my talk today. And tomorrow we will continue. I will remind the results we have already obtained, just in order to be able to follow what follows in there. Thank you very much.